An astronaut of 155 kilograms is floating in space at 6.5 meters per second. He fires a thrust from his jetpack of 220 newtons for 2.4 seconds at 75 degrees to his direction of travel as shown in the diagram. Find his new direction of travel. And the diagram just has a line in which going at 75 degrees, right? So you'd have your astronaut and his added momentum. So first let's draw our own diagram to sort of demonstrate what's happening. So you'd have the astronaut's original momentum, and we can draw a vector because we have a direction and a magnitude. So that's why it works. And we're going to say this is at 0 degrees because we're not given any direction, any specific degree or specific direction. So we're just assuming it's at 0 degrees. Then you have the change in direction. So you have, or the change in momentum, sorry. There's an added momentum, and it's going at 75 degrees, right? So you'd have this 75 degree angle here. And finally, to find the new sort of the momentum after you add the change in momentum, you just draw a line here to here. So to demonstrate this as an equation, we would say the initial momentum plus delta symbol. The change in momentum is final momentum, and I'll just draw in the I and the F. So initial momentum plus change in momentum equals final momentum. This makes sense because this astronaut is going at an initial momentum. He has a mass and velocity. Then there's a force being applied over time to him, so that's an impulse, which is change in momentum. And so they add together to find the final momentum, right? So this is step 2, this is step 1. We still need to fill in the rest of our data. But yeah, let's just go ahead and find the data. So initial momentum, what is his initial mass and initial velocity? Well, his mass is, I think, it's constant. It's 155 kilograms times, what's his initial velocity? 6.5 meters per second. Okay. Let's see, 6.5. Right, so that's his initial momentum. And for that, we have, and I know I'm not breaking down exactly how we'll find his new direction yet, but I'll get to that in a second. Okay, so you have this information, and the initial momentum equals 1007.5. Actually, I'll just do something very fast. Okay, not that. I'm not going to do that. Okay. Let's move this down here. Okay, let's just do that. And let's enlarge it, because there's something important I'd like to show. So we can, to find direction, we're just going to work with the vectors here, and I'll draw out what I mean. So what is the direction? What's the final momentum's direction going to be? Well, it's going to be this angle, right? So in order to find that angle, we're going to basically find what we're going to find. Okay, just to break it down very fast, we're going to find the x component of this and the and add that to the momentum here, the initial momentum, and find the y component. So we're going to add I'll just draw that as a formula here. I'll delete that because we don't need it. Delete these. Okay. So our formula for the, or just the length I'll draw is pi plus change in px, and this is py. Okay, so that's the sort of breakdown. And what is, how do we break down change of p into change of momentum into x and y components? We'll get to that in a second as well. So yeah, again, make sure you've written the formula down, but I'm going to just delete this, and let's now draw another diagram, because in physics we love diagrams, to demonstrate the force, or to break down the force. And when we break down the force, we can break down the momentum into, we can break down the force into x components and y components, and then multiply those by the times to get the x and y components of the momentum. So let's do that. So first let's triangle. Good enough. I mean, that's pretty good. Let's see. So then you have your, so it's at 75 degrees. 5 degrees. And we have the hypotenuse. So it's 220 newtons, right? So how do we work this? Well, we just use trigonometry, our good friend in physics. I'm just gonna skip all the actual trigonometry and just tell you that f of x is, you should know this is cosine, so f of x equals 220 cosine 75, which, not 25, 75, which in turn equals around 56.94. In my calculations, I actually used the exact amounts, so my calculations might be slightly different from yours if you round yours, but it's no big deal. Just an error of like 0.01% or 0.01 won't kill anyone. Okay, and then this is going to be signed because it's the opposite here. And that's going to equal 212.5, right? So these make sense, but how do we translate these into the change in momentums? Well, we just multiply them by the times. So then, since change in momentum is force times time, and the time is, I'm just going to make sure it is 2.4, yes, it's 2.4. We get the new values here to be, let's see, 136.65, and that goes on as a never-ending decimal. Well, it probably ends sometime. And this you get around 510, and then 0.0 something something something. So yeah, that's, here we have the, let's just shrink these. Let's see if we got everything here. Hey, nice. Okay, well, we're kind of missing something. Hey, okay. Let's shrink it down and move it. And we get this being the change in momentum in the x direction, and this being the change in momentum in the y direction. Okay, so how do we translate this into our triangle? Well, first, let's see. I used Okay, so here our angle, for our angle, we have this measurement and this measurement. You can easily do tangent of this angle is the change in py over these. For some reason, I found change of pf, and what did I do? I did cosine. Uh, that's just me being me. I don't know why I did it, but I did it. So, for cosine, or for PF, I'm just gonna say that I found that using Pythagorean theorem, and that is about 1,252.6. If you were going to do what I'm doing right now, I really recommend you use Pythagorean theorem to show how you got the final momentum. And for that, you just say this x leg squared times the y leg squared equals that squared, and you find the square root of that by finding the square root of these squared. It's just Pythagorean theorem again. So yeah, that's that. So the cosine of the angle would be, and I know we're kind of jumping from, so we go from there to there to there to there. So the cosine of the angle we're looking for would be, it is pi plus delta p x over pf. So it's the x, the adjacent leg over the hypotenuse. That's just cosine. So first, for cosine theta, we find that when you add these two together, you get approximately 1,144 point something. It's something that goes on for a while, and there should be a decimal here. I didn't find the first decimal point, but to find that, you just add initial momentum and the change in momentum in the x direction. So you add this to 1007.5. So yeah, if you want to, it's like probably, yeah, it's 1, it's 1, and then it goes on. So then you find p, the final momentum, which we just wrote there. And we're almost done, so we're actually kind of near the end of the time, the 15 minutes I have, but I'm just gonna, okay, so then you find the arc cosine of this, right? So you take cosine -1 of this. So write that in your work. I'm not going to do that because I'm out of time. And you find the angle to be approximately 24 degrees. My question to you is, does this make sense? My answer for you is yes, it does. And the reason for that is because, as I wrote, it's between 0 and 75, and intuitively it has to be between 0 and 75 because you start with the angle of 0 and you add an angle of 75, and you're finding some sort of an average between, not an average, but something that intuitively has to be between the two. So yeah, that's why it makes sense. And that's the final, well, not the final, it's the 9th FRQ, but it's the final FRQ for me to record. So yeah.